My name is Brad Nickerson. I'm the past president and a member of the Jemseg Grand Lake Watershed Association. We are very grateful to Toon for sharing his deep knowledge and passion for the geology and natural history of New Brunswick with us this evening. Our watershed covers 3,950 square kilometers, which is about 5% of the area of the province of New Brunswick. And it's a sub-watershed of the 55,000 square kilometer Woolastook or St. John River watershed. Grand Lake at 171 square kilometers is the largest freshwater lake in the Maritimes. If you're not already a member of our association, we invite you to join, and memberships are $10 per year, and support our activities, including the organization and hosting of this webinar. And if you visit our website, there's a little blue Join Us button on the upper right-hand corner. You can press to join. We welcome your questions. Please use the chat window during the talk to ask any questions as they arise. If you wait, you'll probably forget them like I would. But you can, if you stay to the end of the presentation, we're going to have a complete question and answer session. And Toon will try to answer any questions that couldn't be answered during the webinar itself. And due to the time limits we have, we might not have time to answer all the questions during the webinar. But any unanswered questions are being recorded in the chat window. So if you type them in, we'll have a record of them. And then we'll try to answer them. We'll get an answer for you via email after the webinar. So as we go along, just type your question into the chat window, and we'll keep a record of it and follow up if we can't answer directly in this live presentation. Okay, we're going to have just a quick poll here now that will ask a question that will make it a little more evident to who the audience is and what they know as far as background in geology. And I'm just going to post a little poll. This one's called About Deltas. There's one question, and you can answer one of 4 answers just by pressing a button. So I'm going to launch this now, and hopefully everybody can see it. And if you just take a second and press one of those 4 buttons about deltas, as we just, in the next 30 seconds or so, this will help Toon, the presenter, actually understand a little better who knows what, who's attending as far as the overall percentages. Yeah, so just take a second and briefly read those questions, and maybe click one of the answers that makes the most sense to you. And I'll wait another 5-10 seconds or so. We're about 80% of the attendees have answered right now, and we're at about 55 seconds. I'll just wait a few more seconds. Maybe some last minute answers will come in. Okay, I'm going to end the poll right now, and I'm going to share the results, and you should be able to see what people answered. Toon, can you see that?
Yes, I can see that.
Okay.
That's pretty good.
Yeah, there's only a few, 6 that don't know about deltas. They think they're perhaps part of an American airline company, but this was just a joke question. When I used to write questions for my students for exams and tests, there's always an obvious joke question. Okay. We're going to end that poll, and I'm going to do one more poll. This poll is a little different. It has slightly different perspective. This one was about deltas. And this poll is called Ice Age Ice. And if you could answer the question, do you know where the ice came from during the last ice age and how thick it was? And again, if you could just click on one of those 4 answers, that will give Toon a bit of an idea and of who's attending and what you probably may or may not know about the ice and the ice age. And most of us, I'm probably I haven't even seen the Ice Age movie, so I'm very far down on the knowledge level on the Ice Age ice. Okay, we're at 52, 53 seconds. We've had 88 answers, 89, 90. We're at almost, well, wait till we go a few more seconds here. Okay, we're about 90% of the answers, people attending have answered the question. And I'm going to end the poll here now and share the results. And you can see that Ice Age ice. So the majority seem to feel that they know few details about it. And there's a few, 28% know how thick it was, how it was moved, how it moved, where the mammoths roamed, and the whole bit. So we have some geologists attending, I would say, Toon.
Yeah, there's a few.
Okay, I'm going to end the poll. Well, thank you very much, everybody, for doing that. Appreciate it. So, just a brief introduction to Toon. Toon Pronk was born in Soest. I'm not sure if I'm pronouncing that right correctly, but that's the way it came out, in the Netherlands, about 40 kilometers from Amsterdam, and graduated from the Free University of Amsterdam with a Bachelor of Science in Physical Geography in 1979, Master of Science in Quaternary Geology in 1983. And part of his master's thesis investigated sea level rise and salt marsh stratigraphy in the Bay of Fundy salt marshes. He spent most of his career since 1989 with the province of New Brunswick as a geologist / geochemist, focusing on soil chemistry, glacial geology, and landforms. One of Toon's career legacies is an extensive province-wide till depth geochemistry and lithology database with over 25,000 soil pits used by the New Brunswick Departments of Transportation and Infrastructure and Environment and Local Government, as well as companies, mining companies, and Health Canada. In 2021, Toon received the Atlantic Geoscience Society Lane Ferguson Lifetime Achievement Award for Outreach and Education. And he's continuing to share that outreach activity with us this evening. He also co-wrote the Ice Age chapter for the second edition of The Last Billion Years, a geological history of the Maritime provinces of Canada, published in 2022. Okay, Toon, I'm going to turn it over to you. And if you could share your screen, we will begin your presentation now.
Okay, so I'm going to have a really difficult job trying to cover about 1 billion years in 40 minutes. So I am going to do a lot of fast forwarding, and this is a very timely story. I guess this is Grand Lake. This is actually taken from the Twin Bridges during the fire of 2017, and this is not fog. This is like actually smoke that's hanging over the connector between Quapac and Grand Lake. And I guess that's the calm before the storm. And so one of the ways to get to know a place is to visit it often and to go swimming and hiking and paddling and sometimes working. And I've actually skied on Grand Lake too. So I've covered all the bases more or less. So we're going to go really fast, and we're going to cover 1 billion years. And we're going to talk about basic concepts for a while and processes, sort of like a geology 101. And then we're going to rely a lot on this book, The Last Billion Years. And it's full of photographs of rocks and landscapes, maps. And it's full of stories, and it's also full of squiggly lines. Like geologists, they like squiggly lines because they like to put things on graphs. So we're going to sort of do a few pauses around 1 billion years. Then we're going to fast forward to 360 million years ago. And then we're going to go to 2.6 million, which is sort of the start of the ice ages. And then we're going to jump to the end of the ice ages, and then we're going to see what kind of impact people have on the landscape. So we're going to talk about supercontinents and microcontinents, timelines, ice ages, and water levels. And I want a special thanks to Serge Allaire, one of my colleagues at the branch, my wife Shelley for technical support, especially last week, and for Brad for general support. So the Grand Lake watershed is somewhat unique in that it has the warmest climate of the entire province. And as Brad said, it's very large. And the watershed is intricately related to the Carboniferous Sedimentary Basin. I will talk a little bit about the basin in a bit, talk to you about what sedimentary rocks are. But watersheds have a very different role in different jurisdictions. I know in the Netherlands, there are water boards that have a very prominent role to play in the management of your drinking water, your surface water, safety for flooding, and a lot of your taxes will go directly to the water board. And then there's the Waterscape, and my friend Antoine, who's online too, he introduced me to this concept of a waterscape and what that entails. And I will talk a little bit about that. So this is the waterscape sort of issue, or it's more like a methodology or a concept, and it relates the surface water and the groundwater with the water in the atmosphere and the water in the biosphere. And it's influenced by all these different levels of the natural landscape. And it's influenced by the temperature, it's influenced by the ecosystem, by hydraulic conductivity and gradient within bedrock. And so it is a very complicated process, but it's important for us that we recognize how that works. And as I said, the basin or the Grand Lake watershed is closely related to the Maritime Sedimentary Basin, and that will come out in this talk, hopefully. I'm going to show quite a few images like this, which are LiDAR images. And LiDAR, not everybody would be familiar with that. A lot of geologists would be. And it's flown from an airplane. It's almost like aerial photography, but it detects the light and the rebound off the landscape. And it will give you an image of the landscape in very, very minute detail. And you can zoom in and out on this, and that's a problem with PowerPoint. It's hard to do that. But I'll have a few close-ups and I'll zoom in on some of these things, and I'll show you some of these kind of features. This is the head pond, the Macquac head pond right here. And you can see this is the old way the St. John River used to flow this way. And this is Fredericton right here. And you can see all sorts of neat features here. There's bedding in the Carboniferous Basin here, which you can see in the landscape. These are drumlins, and you can see them, and those are glacial landforms. This is the drumlin that's at the agricultural station on the St. John River, and this is a 4-kilometer long ridge of glacial material. You can see fault lines. There's a fault line coming in here. This is Killarney Lake, and this is the Fredericton Escarpment and the Fredericton Fault. This is a delta that belongs to the Keswick River, and this is like a pro-glacial meltwater channel. And this is an oversized valley. So now the stream that's in there is very small, but the valley is extremely wide. And one of the attendants actually lives right on the ridge and has a beautiful view down into this valley. So yeah, you see, you also see moraines. There's moraines all the way through here. And I'm going to talk about moraines a little bit later as well.
Toon, we have one comment from a gentleman who can't see your pointer. Is there any way you can make your pointer a little larger? There. Oh, okay. Yeah.
How do I make my pointer larger?
I don't know the answer.
Maybe I'll move it slower. Does that help?
Jim, can you type an answer there? Does that help your, try the highlighter selection. Okay, whatever that means, highlighter selection. Okay, Jim said it made it better when you moved more slowly.
Yeah, I'll keep it red. So anyway, okay, so here I'll move it slow. So this is a picture of the province, and it's the very complex geological picture of the province. And basically, this pink area is the Carboniferous Basin. And this was formed during a period between 360 million years and 299 million years. And this was part of a big river system that deposited all these conglomerate, these gravels and sands and silts. And we're going to look at some of this in a little bit more detail. And it was distributed, and it was flowing out towards what's now the northeast. And now the drainage goes down this way. And this is very important with how the water flows like in the basin, and it congregates towards the center axis of the basin, which runs right through here. So I want you to remember this pink wedge, and we come back to that later.
We have one more comment from Jackie. She says, or he says, select the arrow to have it set on the pen, and that might make it a little bigger.
Arrow?
Arrow, yeah. Try that.
This?
Yeah, that's bigger. Yeah, that's looking
Okay.
better now. Yeah.
I like my pointer better, but I will work with this. So
Yeah. It makes it more visible to people with smaller screens, I think. Yeah.
Yeah. So I'm usually used to bigger screens, right? So how do continents form? And continents, well, there's a First Nations story about Turtle Island and how the otter brings the mud onto the turtle's back and things like that. And I would say that's a very simplistic way of accretionary terrains. And so in geology, we see that there's volcanic islands that are formed over subduction zones. There are volcanoes formed over hotspots. There are mountain ranges that are formed by one continental plate bumping into another and forming mountain ranges. And all these ways in which the different slices of macro and microcontinents come together is how large continents are formed. And that's usually how supercontinents are formed. And I'm going to talk a little bit about the supercontinents because that plays a big role in the formation of the basin. And so it starts 850 million years ago. And most of, like I said, most of these slides are from last billion years. And this is Laurentia. This is part of northern Canada. This is Hudson Bay here. This is Greenland over here. This is, I think that's the St. Lawrence River right there. And this is the Grenville. And when you drive through through the St. Lawrence Basin and into Montreal and then to Toronto, you drive through all these red rocks, basically. At this time, Fredericton was like not really the Carboniferous Basin, which Fredericton lies in, was not even present yet. St. John is sort of on the edge of this continent, Baltica, and there are rocks, the oldest rocks or some of the oldest rocks in New Brunswick are in St. John, and they're 850 million years old. They're exposed at the Reversing Falls. And there's only one place we know that we have older rocks, which is White Island off Graminan, which are 1.2 billion years old. So this is part of an older supercontinent. And so we fast forward 500 million years and we go to the most recent supercontinent, which was Pangea. And during this time period, as you can see, this is Africa here, this is South America, this is the Canadian Shield. And in this zone here, all these small microcontinents are basically pushed on top of each other and there's volcanism happening, but there are also sedimentary basins. So there's large rivers that carry lots of sediment from these mountainous areas and that are deposited in the lowlands. And so during this time is when the Carboniferous Basin was formed. It was formed somewhat between 360 million and 300 million years ago. So that's it. And this is sort of what it looked like. These are mountain ranges, and these are the ones that I showed on the last ones, and there are these little slices of continents. And so those are the Appalachian Mountains today. But the basin that's in between those mountain ranges, so this is like the Caledonia Mountains over here, and this is the Miramichi Mountains over here, the highlands. And the source for all the rocks and all the sediment that's deposited in this large basin come from these mountain ranges. And this yellow part here is the shallow part. And I think if you can see that, it's 0 to 2 kilometers in thickness. But most of New Brunswick, actually, the Carboniferous cover is less than 500 meters thick. And that doesn't seem like a lot to geologists, maybe seem a lot to you, 500 meters, but on a global scale, that's not really that deep. As you can see, the deepest part of this basin are 10 to 12 kilometers, and they're in the north of the Magdalen Islands. I have to look at my notes every once in a while because I have a tendency to keep talking and forget what I really want to point out on the slide. So this is what the Carboniferous Basin looks like today. It's all these remnants in yellow, and you can go to Plaster Rock. There's a little piece of a Carboniferous Basin there. You can go to the Gaspé, and there's a few slices of Carboniferous there. All of PEI and all of the Magdalen Islands are Carboniferous. As you go from the southernmost point of the Carboniferous Basin, which I'll have on a future slide here, and you go to the northeast, you go from really coarse sediments. So like along the edge of the basin, there are conglomerates, which are basically hardened gravels. You go to coarse sandstones, and then you go to finer sandstones. And as you come to PEI, you find out that there's mostly very, very fine grained sandstones and also fine grained silts. And then as you go farther into the basin, the sediments gets finer and finer. And that's just, I guess, a result of the physics of the energy that's waning as you go to the northeast. This slide on the inset is what the Carboniferous landscape might have looked like. And you see all these river systems, and they all flow to what is now the northeast. Of course, this happened while New Brunswick was still south of the equator, and it was just slightly south of the equator. So the temperatures were hot, and it was probably very humid. And this is sort of where Grand Lake is. And now, of course, the drainage for this area goes to the south. And this has major implications because it's blocked by these rocks that are in here, which are way more resistant. And we'll talk about that in the context of flooding and restrictive valleys. So this happened during the end of the Permian and the beginning of the end of the Devonian and the beginning of the Permian. So for about 60 million years, this was going on. So how did that happen? And somebody earlier asked how we form coal and why you find coal in certain places and you don't find it in other places. Well, you have to think about, like, even today, you have levees in the St. John River system, and you can see it, for instance, around Sheffield. The old Trans-Canada Highway was built on one of these levees, right? And then you have the backwaters where you have formation of peat. You have rising sea level, you have sediments over top of that. You get burial, and then the sea level retreats again, and you have these cycles, and so you form these layers of coal, like in between the sedimentary rocks. Now, the coal layers in the Minto area are not very thick, and that's why we don't mine coal. That's one of the reasons why we don't mine coal there anymore. This is sort of what the Carboniferous ecosystems might have looked like. These back swamp areas where you have like really, really large horsetail, like almost tree-sized horsetails. And when these die, they fill with sediments and they fill with fossils of like animals and things like that. And that's when you can find things like this. So this, again, this happens between 360 and 300 million years ago. So this is that slide from the southernmost part of the Carboniferous Basin. And this is a LiDAR image. And you can see a lot of detail on this. You can see the bedding in the Carboniferous, which goes this way and it loops around this way. And then these rocks here, they're very, very resistant, and they're conglomerates and they're quartz sandstones, some of the Boss Point formations in here probably. These rocks here, though, are not Carboniferous, and they're volcanic rocks. They probably, they might be like early Carboniferous, but most likely they're late Devonian. And these are very resistant. And as you drive over certain parts of the Hanwell Road, you can see some of these cuestas in the landscape, and there is very, very specific landforms, because the back slopes of these are related to the bedding in the Carboniferous Basin, which almost goes horizontal here. You can see drumlins again. This is a glacial feature. All these elongated landforms that are here. Some of them, there's very fine ones in here, and they go in a different direction. So the ice flowed in different directions at times. This here is a granitic terrain, which you can see is a totally different kind of relief. This is the Oromocto River, and this changes into the Nerepis somewhere down here. And so at one point, this was actually a pro-glacial meltwater channel instead of the St. John River that we know today.
We have a question, Toon. He's from Ailra. He or she asks, what explains the sawtooth pattern?
The sawtooth pattern here?
Yeah, I would think that's what, yes.
It's probably partially weathering and glacial erosion, but it probably also reflects some of the hardness of some of these volcanic rocks, or the conglomerates in this case here.
Yeah.
And the way the drumlins are often formed, they also formed like in fields, and that is related to the pressure underneath the glacial ice. So it has a totally different kind of origin, I guess. I hope that answers part of the question.
Yeah, that's good. We have another question. Just amazed that New Brunswick was south of the equator at one time. I think you mentioned it briefly, but true? Yeah.
Well, because the continents have moved basically all over the planet over time. I think if you look at the Canadian Shield, it's covered like every part of the globe almost, it's wandered all over the place. And during the Carboniferous, we happen to be just south of the equator. Yeah. Okay. And I might come back to that later a little bit.
Okay, thank you.
So when the Carboniferous era was over, I wouldn't say we went into a hiatus, but there was not a whole lot of deposition going on within the province. There was the next major event that happened was when Pangea started breaking up, and this is what's now the mid-oceanic rift right here, and Iceland probably somewhere up here now. It wasn't there at this point, obviously. But before this broke apart, there was a rift zone that went right through here into the Bay of Fundy. And that rift somehow started, and it has a lot of volcanism associated with it, like all the basalts on Grand Manan, on Ile Haute in the Bay of Fundy, and the North Mountain basalts, like up in Nova Scotia. They're all related to this rifting. But for some reason, the rifting stopped, and the ocean, or the Pangea, broke apart over here, and this is where the Atlantic formed. And so Nova Scotia could have been part of North Africa instead of being part of North America. And the rocks on this side of the Atlantic and in Morocco on this side and in part of Spain on this side are very, very similar. So it's, again, the continents have moved a lot. So fast forward again, because as the continents started moving again, and initially this happened quite quickly, but there's periods when it moves faster and some slower. We're not quite sure why. But right now, the Europe and North America are moving apart at about 2 centimeters a year. And that doesn't seem very fast, but it's over time, it sort of adds up. Because when I fly home now, it's a long way, you know. So what that resulted in was in the present day pattern of the continents. And why is that important? Well, it's important because there are other things playing in the realm of the solar system and the planet Earth, and they are all related to the ice ages, because you need a certain configuration of the continents to create ice ages both in the north and the southern hemisphere. And in the northern hemisphere, you need like an open Arctic Ocean like this. This is one of my favorite maps, by the way. This is the International Polar Year. I think it was 2001 or something like that. And in this map, you can see if you have an open Arctic Ocean, you can get all the North Atlantic or the warm water from the current. You can go right through here and can enter the Arctic. And what it does, it melts more ice and snow, but what it does, it also creates more evaporation, and it creates more precipitation on land. And if you are in the right kind of setting and in the right kind of radiation regime, like between the planet, our planet and the sun, you can have ice buildup in this part of Canada and Beringia and in northern Scandinavia. So that's why that is very, very important, where the continents are at a specific place, time and place. So what causes the ice ages? Well, there's something we know as the Milankovitch cycles. And the Milankovitch cycles, they are the relationship between our sun and the planet. And this is the planet's orbit, and it goes from very elliptical to more like a circle. And you see the sun is not in the center of this. So it makes a big difference as to if you're farther away and close by. And this cycle, we call it the eccentricity cycle, takes about 100,000 years to complete, and then it goes back to its origin. And then there's the obliquity cycle, which is the Earth's axis goes from 22 degrees to 24.5 degrees. I think we're about 23 right now. And so it goes back, the axis goes back and forth a little bit. And then there's a third cycle, which is a lot shorter, which is about between 19 and 20 years, so about 20,000 years. And it's the wobbling of the Earth. And this has also an impact because is our pole, is it pointing towards this? Is the North Pole pointing towards the sun when we're closest, or is it pointing away from the sun when we're closest? And so this all has an impact on how precipitation lasts in the northern hemisphere and how you have ice buildup and how you get glaciers. So these are some squiggly lines, and 2.6 million years ago, that's the start of the Quaternary. And as you can see, the cycles here at the beginning, they're all about 40,000 years until about 800,000 years ago, somewhere around here, something changes, and we're not exactly sure why. But so this is dominated by that 40,000 year pattern, and then all of a sudden, this is dominated by the 100,000 year pattern. And since about 800,000 years ago, we have had 8 large expansions of ice sheets. And some people like to call them 8 ice ages. I like to clump them together, and it's the Quaternary Ice Age, because there were ice ages in the past. At one time we had, we called it snowball Earth, you know, and the glaciers were extending way farther than they are today. So as you can see, almost all of Canada was covered by ice, except like part of the Yukon, which seems kind of weird because that's a colder area, right? But very dry up here, you know. Must have something to do with the circulation of the air. And so ice buildup in this area was tremendous. And we have calculated through geodesy and stuff like that, that the ice here was probably somewhere around 3.5 kilometers thick, which is, ice starts flowing under its own pressure at about 60 meters thickness. So 4 kilometers of ice, you have a lot of flow going on. It starts to behave like molasses, right? So you can see these are flow lines. You can see they all go down. This is the corridor between the Rocky Mountain ice sheet and the Laurentide ice sheet. And at some points, this sort of opens up a little bit, and there's all sorts of theories about people moving through here. But I think the more accepted way people moved into North America now is along the coast, starting from the northwest. This is Fredericton, this is New Brunswick right here. So what did it look like in more detail? Well, this is, I think this is also in the last billion year book. And these are ice divides. So it's like almost like a watershed, you know, like the ice on this side flows this way. The ice on this side flows this way. This is the maximum extent at 20,000 years. And then you can see that these flow lines, they sort of all terminate in the North Atlantic. But there's a big ice stream through here where the St. Lawrence River is today. And there's a calving bay here where we have lots of icebergs coming in. And we don't know exactly how fast this flowed, but this drained a major part of the ice sheet that was over Ungava Bay and Hudson Bay. So we're not in New Brunswick. The ice was probably somewhere between 750 and 1,000 meters thick. So how did, when we were the maximum extent, George's Bank was like probably possibly ice-free, and part of the Grand Banks off Newfoundland was possibly ice-free. And these were sort of anchor points for the edge of the glacier. And we see some of these things now in Antarctica. And some people think that the squirrel was responsible for the end of the ice age, but I think it was just major warming. This squirrel is not geologically accurate anyway. We have like a big fanged squirrel-like creatures back like 94 million years ago, I think, during the Cretaceous, but nothing like this during the Pleistocene. So when the ice started retreating further and it started melting, these ice divides, they changed their configuration, and ice started flowing in different directions. This is the Chaleur Bay down here. Mike, who's also in on this talk, he lives right here in Bathurst. And there's all sorts of really, really neat features in the northern part of the province that you can trace how the ice exactly flowed and where the drumlins form, because they give an indication of where the ice moved. And so then when it finally went, people moved in. This is at 12,000 years ago, well, 14,000 years ago, calibrated, I guess. But at about 11,600 years ago, people lived, or they had an encampment at Marysville on the delta, on the beaches there, just close to the bypass. And that was just excavated here about 7-8 years ago. So people were already in the landscape when ice was still present. There was a lot of food around, like the caribou herds, mastodon. There was all sorts of, big game around. So then when the ice finally disappeared, well, yeah, New Brunswick might have looked something like this, big ice streams, peaks. This is actually an ice front, but there are peaks sticking out through the ice. This is the Beardsmore and Mills glaciers in Antarctica, but you can imagine the landscape might have looked something like this. So what do we find in the landscape? In the landscape, we find all sorts of indications of glacial activity. And there are these kind of outwash plains, and I talked about them a little bit. I probably could have mentioned a few more on the LiDAR images. There are drumlins, I pointed those out. Most of New Brunswick is covered in a layer of morainal deposits, which is glacial till. And that's where we have a gigantic database for all these soils that formed on this material. You can find lots of landforms like this, or striated bedrock. And you can find striated bedrock in the Grand Lake area, but it's usually a lot more horizontal and they weather a lot easier. So once they're uncovered, they disappear usually quite rapidly. But as you can see, stones are the most interesting things in the world, and I agree with that. So when the ice retreated, the water moved in, and somebody asked a question about the difference or how much of this was isostatic, which means the crust, because there's a lot of ice on the crust, and I mean, the ice here was not really that thick, but if you go a little bit north of here, if you go north of the St. Lawrence River, the ice is probably still like 2.5 kilometers thick. So there's a lot of weight on the crust, and the crust is depressed. Once the ice melts, the crust will rebound. It will float back up, but there's a delay there because it doesn't react so quickly. But the water is reacting really rapidly because it's melting, and you have large, like the Agassiz, Lake Agassiz, for instance, which is on the prairies where Winnipeg is, and it drains into the Atlantic Ocean, and ice from everywhere drains into the Atlantic Ocean. Sea level rises and the water moves in really, really rapidly. And so this is what the blue material, or the blue area here, that's around the 70-meter line. So all that was probably underwater. These red triangles are glacial deltas, and I'm going to talk about that a little bit later. And somebody also asked, like, if there's a difference in the rebound. And if you go up to Keswick, there's delta levels, top sets. The top of the deltas are at 80 meters. But if you go towards the coast, you can see they're less and less, because there was a lot less ice to the south and a lot more ice to the north. So the rebound is a lot more up here, but the crust was also more depressed. So the water moves into the landscape a lot further. If you go to Nova Scotia, you end up in deltas at like 30 and 40 meters. So it's quite significant. So what kind of other landscape features do we see? Well, we see moraines. We see some moraines down here. And I think actually that I looked at it in detail, and I think it's a moraine that's down here. That's Grand Point. There are other ridges that are moraines, but there's these lines in the landscape over here, and this one over here, and there's a whole bunch over here. And those are all strand lines. And strand lines are basically old beaches. And so all these beaches, they indicate previous water levels during early post-glacial times. We see the levees here, the old Trans-Canada Highway. This is the new Trans-Canada Highway, which is built its own levee by people. And there's drumlins that we can see down here. There's another interesting feature down here, which is the island, Gagetown Island, and where the old homestead is built on. And I think that is also moraine. So there used to be probably an old morainal ridge that crossed the valley here, which is mostly eroded, but there's a little remnant left right in the center of the island, and it's got some very, very interesting features there.
Toon, could I interrupt just for a second? We have a question, phrased by Ailra Chasson. If you put a lot of pressure on a balloon, it eventually ruptures. Why didn't the glaciers cause the same thing to happen to the crust? maybe leading to volcanoes?
Oh, well, it's basically just a transfer of weight, right? Like the weight was already in the oceans or in the atmosphere, and we just transfer that weight onto the land. So really, and there is a bulge, like when you look at a glacier, and you like sit on a waterbed and you jump on a waterbed, there's a bulge outside of where you're sitting, right?
Yes.
So the weight of the glacier creates a bulge all around it,
Okay.
but it doesn't explode. Like the Earth's crust is actually quite flexible, you know. So yeah, it doesn't explode.
Isn't there a volcanic remain in Douglas area near Fredericton? Is that
There
true?
is some volcanic rocks at Curry Mountain, yeah, and
Yeah.
those are the same. They're the same age as the volcanic rocks along the Harvey Lake area.
So
Yeah,
that wasn't a result of that depression.
Yeah,
Actually.
that's right.
Okay. And we have, yeah, so the inland water would be salt water. Is that true? And a question.
Yeah, it would be estuarine, so but it would be very diluted with the meltwater, right? So there would be a lot of fresh water coming in.
Mhm.
So it would be probably brackish, yeah.
And does that explain the potash deposits and salt in the Sussex region?
The potash deposit in the Sussex area are the result of evaporites that were also formed during the Carboniferous when we were south of the equator. And you know, when you look at flamingo movies and stuff like that, they always are in these salt lakes.
Yes.
Yeah, and there's evaporation. So the water evaporates, the salt stays behind, and then it gets buried.
Okay.
Yeah. So one of the sorry.
Yeah, that was it. That was the answer.
Okay.
Thank you.
One of the man-made features here is this new Trans-Canada Highway, and as you can see, that's like a dike. And I was joking with Brad last week that this was actually engineered by a Spanish engineer. Now, if they would have hired Dutch engineers, they probably would have put a big part of this on stilts, because what you've done here, the water comes into the Grand Lake watershed here at Sheffield, where it goes over the levees, and then it tries to get out. But here you have restricted the valley. And this is just creating an extra bottleneck, because there's tons of bottlenecks further to the south, which I'm going to talk about a little bit later. But this has created another bottleneck, right? So it's a man-made, and not that I'm saying that caused the flooding, but it didn't help.
Mhm.
So this is Gagetown Island, and this is up here where the homestead is built. And you can see these really, really large granitic rocks that are, and they're not just part of they're incorporated into part of the building, but they're all over this ridge that you can find here. And this ridge is probably stands out about 25, 30 meters. It's hard to really see it here, because when you get close, you can't see it anymore. So you have to take the picture off the St. John River. So this is on one of our boat trips last year. So I thought I'd make a picture of it, because but it's amazing that you can barely see it, you know. So that picture was the ridge is right here, and the picture was taken from up here. Yeah. So it's quite a ways away. So the landscape of the Grand Lake area is the sum of the bedrock geology, and you can still also see sorts of landscape features that are related to the bedrock. You can see some of the bedding right here still, right through here. And then you can also see that all of a sudden the landscape changes down to here, and it's a different landscape. The other thing that happens right here is this becomes a bottleneck for water, because you can see how wide and broad the floodplain is up here. And it's because of the Carboniferous rocks. They're very soft, they erode very easily. And so the river has way more room to expand, or is easier to expand. But then it goes into this harder, older bedrock here, and it's a very condensed, or a very constricted valley, they call it. And so all the water, especially when you have high water and it's all in here and it can't go through here. It's like a bottleneck, right? And there's several of these down in the valley. So then you have glaciation, you have all sorts of drumlins. This is the Oromocto River, and there's actually some beautiful drumlins here in the valley. And there's some farms that are actually built on these drumlins because the water around it floods every spring, you know. And so there's a lot of wave washing going on. And then I talked about the human influence. So what else do we see in the Grand Lake Basin? Well, this is Grand Point Bar. And sometimes this is in 2017, I think, or maybe 2018. And the water was really low and you could walk out way into the lake. And this is a little ridge here where this house is built on. And there are all sorts of really strange rocks on the beach here. And if you walk this sinusoidal, people thought it was an esker, like an under ice kind of river that deposited a lot of sand and gravel. But there are gigantic boulders all along the flank of this ridge. And so now we think this is a wave washed moraine. So it's a morainal ridge left over, but it's just very washed on the top. And you can see, like, this was a fairly quiet day, but the waves on this side are just gigantic compared to on this side. There was another day we were here and there was just whitecaps everywhere on this side. And when you go along the beaches here, and we did a survey one time, and you find this one I actually spotted from the water one time when I was canoeing. I said, that looks like a really weird rock on the beach there. So anyway, I went up to it and yeah, it's nothing I'd seen before. And this is a chernokite. And chernokites, we don't have any chernokites in New Brunswick. And one of my colleagues identified it as coming from the Saguenay region. So it's 500 kilometers away. So it came here with the ice. It means that the ice came over top of the Chickasha Mountains. And it followed sort of like this pattern. So the rocks came from here. They flowed down this fjord here. I probably found one of these openings up here, and it probably sheared up into the ice. And some of the ice obviously overtopped this. And we find erratics from this area up in the plaster rock area up in here a little bit, not very often. But when you go to Grand Lake, there's some of these morainal ridges, and they have a ton of them in there. And some of them come from this part of New Brunswick. Some of them come from up here, but some of them come from this area in Quebec. And so they're transported over this distance. And when you drive up to Vierloo, you see some of these lakes in here that you drive past or by. They're very elongated and they're almost like inland fjords. So they're definitely glacial, and these boulders are moved by glaciers. So there was a question about deltas. And so we look at all these deltas that are in this system here, and you can see the highest ones are over here and they go less and less over this way. And I see that it's, I've used quite a bit of time. There's only a few more slides left. So if people are still okay with it, I'll finish my thought. And so you can see that.
Keep going.
I keep going.
Yeah.
So you can see that the delta altitude, like it goes down as you go toward the coast. And I'm going to focus in a little bit. You can see here too that how wide this basin is up here. And then when it goes through these kind of places, how restricted the valleys are. So there's one place, and this is the Blagden Delta just north of Welsford. And when you come from St. John and you look to your right, just before you hit Bald Peak, you can see this perfectly horizontal landscape right here. And that's the top of the delta. And there's a tremendous amount of aggregate in this delta. And this is a pro-glacial delta. So this is all formed and deposited by meltwater from central New Brunswick. And so what's a delta look like? Well, it looks sort of like this. This is just the top set. This is that horizontal piece that you see. And then there's all these foresets and bottom sets, and it's all sand and gravel. But basically, it's pure physics when the water comes down the river and it's laden with sediment. And in a In a glacial environment, it's just loaded with gravel and sand and sometimes even boulders. And as it spreads out in an area like this, where it finds more channels, or it goes to a braided stream, or it drops into a lake, the amount of energy just dropped tremendously, and all the coarse material drops out first, of course, and the finer material eventually drops out too. So this is how deltas forms, and there's a large number of large and small deltas all through this system. When you stand on top of Bald Peak and you look towards the delta is right in behind here. You can see that the St. John probably took this valley here and used the Nerepis River and flowed through this notch here, and that's Grand Bay in the distance, and then flowed further down. There might have been ice or a moraine. Remember that moraine that I pointed out on the Gagetown Island? That might have blocked the water over on that side, or there might have been an ice remnant in that river as well. When you go further towards the coast, you come to St. John, and this is the ultimate bottleneck. At one point, we think that the water probably flowed through South Bay and out this way, but then probably a re-advance of ice, and it formed this moraine right here. And most of the moraines, they're formed at the front of glaciers, and it's basically a big dump of material. And they're usually anchored on bedrock points. And if you look through here, there's all sorts of places where you can find bedrock. But there's a deep channel through here that comes out this is Taylor's Island. It comes out through here, and it probably flowed out this way. And of course, now the St. John River flows through here, which is the Reversing Falls. And we thought, well, maybe after the floods, we could talk about maybe having a spillway here or something like that, but it's extremely expensive. It probably wouldn't help very much anyway, because as you know, we have the Bay of Fundy tides, which are a major obstacle to the drainage of this basin. So this is sort of what this is a confined valley, right? Like it's very restricted. The water level is not very high, but this is what happens when the water cannot drain and it's unconfined, and it finds all the low spots in the landscape. And that's why we have to really seriously think how we're going to deal with that as we expect these things to become more and more frequent. And this is what we do with rivers. And the city of Fredericton was going to build a playhouse right here behind City Hall. Not a good idea. This is the Tantramar Marshes. I think it was 2015, and there was a very, very high tide and a storm, and the water almost overtopped the CN Dike, Railway Dike. And we've been studying this now since then, and we haven't really done anything about it. So some people in my branch say we're playing Russian roulette with the Bay of Fundy, you know, like the next storm and the next timing of a bad timing of a storm with high tides or spring tides might overtop this. It would erode this CN rail line. It would also erode the Trans-Canada, which is right in behind here, you know. So it's very, very dangerous. So what does that mean? What's the climate change in climate, or the rise and the higher tides in the Bay of Fundy mean for the Grand Lake Basin? Well, if you look at all, these are all different models. And I have to say, for the last few centuries, mean high tide in the Maritimes have gone up 30 centimeters per century. So we already have a rising sea level. But then on top of that, we have this happening, where, you know, all these models show that the sea level is going to rise. So if you add this to like the 30 centimeters that we already have, sort of right in the middle, that means we're going to have like probably tide rising by 80 centimeters by the end of this century. What does that mean? Well, because the Grand Lake Basin is basically at 0 meters. And so how do we plan for these changes, right? When people first lived in this area, they lived like this, and they could, you know, they were very mobile. These people figured out a way to escape the water This might be a good way to, if you want to live on the lake, this might be actually a very, very good way to live on the lake. You can adapt. This is the Beaverbrook Art Gallery. And I was mentioning to Brad last week, these are called Dutch doors. And they basically close when the water pushes onto the doors and they seal themselves in the back here. And these have been used in dikes in the Netherlands for centuries and very effective. So you can adapt. But you have to start looking at the landscape in a different way. And this concept, the critical zone concept, it talks about how we are connected to the landscape in all these different ways, and how we deal with that, and how we're going to react to the challenges that are ahead. And so now that we have a feel for the place, what would we do? And this is my last slide, I think. Oh, no, this is my last one. It's my before last slide. And if you haven't watched this Netflix documentary, I suggest you watch it. It's really good. It's about an hour and 15 minutes. And it comes from research that was done by the Stockholm Resilience Institute. One of the first time I saw this was in one of the talks by Antoine, who's online. And this explained in its documentary that this is the Holocene, which is the last 10,000 years. And basically, the Earth's population and civilizations have really all happened in this last 10,000 years. And climate, even though it's gone up and down a little bit, has been very stable. During these periods here, there was tremendous warming. We had, the megafauna extinction at the end of the Ice Age. We had sea level rise. We had all sorts of different things happening. What's going to happen here? Well, we know it's going to change, but we just don't know how these things are all going to affect us. And this documentary will show you some of this. And as you can see, climate change is not our main concern. There's things like ecozones or ecological changes and genetic diversity that are really important. The other thing are nutrients that we put in the environment. And so what are the things that we can do both as individuals and as a society and maybe as a watershed? Like, how can we approach these things? And then I want to end with this slide, which shows you how the warmth that is created really dissipates throughout the oceans and over the entire northern hemisphere. And so when you have a lot of warm water here, you have more melting, you have more influence of warm water in here, you have more precipitation, and eventually, yeah, you might have a new ice age. But that's going to take, maybe another 50,000 years. So, not what we want to wait for. All right.
Okay, that is wonderful, Toon. I appreciate very much your presentation. We have some questions that were asked, and I couldn't interrupt you at an appropriate time, so I'm going to go back and do them in order. If you're willing to answer, there's about, let me see, half a dozen questions. Would you be okay to answer those?
Yeah, sure. Let's see
okay. Yeah. A question from Mikael Gullström asks about the basalt formations on the Digby Neck. Are they from this period, which I assume would be the Carboniferous period?
No, those are Triassic.
Okay.
They happened when Pangea broke up. When Pangea broke up, and there was all this volcanism happening. It's like a rift zone that's happening in Eastern Africa today. And so you have all these volcanic eruptions and these basalt formations, and very often they're pillar basalts that you can find on places like Eel Hout and Graminan. If you go to the south point on what's it called, Southern Head, you can look down by the lighthouse and you can see those basalts. And those are the same basalts that you can find at the North Mountain basalt at Digby. So yeah, they're related to the rifting of the Bay of Fundy.
Okay, so it was earlier than the Carboniferous period then.
Later.
Later. Okay, great. All right, that's excellent. So a question from Chelsea also, does that mean, this is about the isostatic rebound after the ice left? So does it rebound in the opposite direction instead of being depressed when New Brunswick had more land? In other words, is there a sort of a rebound that I think we're in a deep, it's still decreasing, right, at this point?
Yeah, yeah.
But did it ever rebound higher than it is now, for example?
Yeah. Okay. There's a specific science. It's called geodesy, and it relates to the surface of the Earth as it's related to gravity, and yeah, I guess it's sort of like a 0 point. And as the rebound happens, the Earth's crust almost behaves like a guitar string. So if you strum your guitar and it will go one way, and then it will go back up a certain way, and then eventually it will find an equilibrium, right? But it will go back and forth several times. So we are still actually our what do we call it, proglacial forebulge is still collapsing. And that's why we already have this 30 centimeter sea level rise over a century, continuing for the last centuries.
Mm-hmm.
So yeah.
At some point it will reverse then and start to go up, is what you're saying.
It will go up when a new ice front comes closer to New Brunswick. Yeah. You'll have this forebulge and it will come back up.
So quite a long time.
The crust will be depressed. I always use my hand, or even if you're in the bathtub and you have something that floats, and you put a weight on it, it will sink, right? Or it will go down a little bit. If you take the weight off, it will go back up.
Right.
Right. So that's what you do with ice. You load it and you unload it.
Mm-hmm.
I'm not a geophysicist, so I'm just like my way through here.
Okay. So it's a complex story, really, when you get right down to it. Yeah. So I have another question from Chris. Chris asks, I would like a layman's explanation of how the Grand Point bar is formed and remains. Why doesn't it just wash away under storm action and things?
That's a good question. I think part of it probably has washed away. Because it doesn't cross the entire lake anymore, right? It only goes about halfway.
Yeah, that's right.
I think one of the reasons might be that the core of the point might be very coarse, so it might be very, very large boulders. And when you walk, when it's really, really low water level, and you walk along the edge of the point bar, and you look down into the water, you see gigantic boulders, like car-sized boulders. So I think, and I mean, maybe we need some more research into this, and maybe some more people can scuba dive down there. I don't know, but I think that's part of the reason why it's still there. If you follow onto the land, and there's a little ridge, there's a house on top of it actually, and initially we found all these boulders like right on the shore, and some of them are very, very large. So I think that's the reason why it's not totally eroded.
Okay, so these large rocks are helping protect it from erosion.
Yeah, and it might be very coherent because maybe it's a mixture of clay and boulders. And,
right. Yeah. Okay. Yeah. Next question from Ecoregion. One of the sketches had kettle lakes.
Kettle lakes. Yeah.
Kettle lakes. Do we have them in New Brunswick? And if
yes,
so,
we have kettle lakes in New Brunswick. We have kettles mostly on deltas that are close to the Bay of Fundy. Like if you go to Penfield and St. George, like there's deltas there. There's one delta actually that has an old airfield on it, but there's a lot of blueberry fields down there on these deltas, and some of them have really, really deep holes, and then sometimes there's ponds in it. And what kettle holes are, they are remnants of big, basically chunks of ice, almost like an iceberg that sort of gets stuck in the sediment, and then the sediment starts get the deposit all around it, and maybe even on top of it, and then the ice eventually melts, and because there's a vacuum there, it will create a big hole, and we call that kettle holes.
Okay, never knew they existed, but yeah, thank you. All right, the next question from Angela. Question about Princess Park area. Is that a moraine or a man-made berm that's been created with development?
No, that's a spit. It's a sand spit, and it's formed by lateral currents along the shore of the lake, and it has carried with it all this sand, right? And so, and it makes these beautiful curves, and it comes out in a point, if I remember correctly.
Yeah.
And it's all very fine-grained material. And so, no, it's not a. And we looked around there for erratics, glacial erratics, and we didn't find any. We found a lot at Rocky Point, and then on the other side of the lake at Cox Point, we found a lot of glacial erratics.
Okay.
Yeah, but not at Princess Park.
Okay.
So those are natural spits, but they're formed by wave action. So that tells you how low they are in the landscape, right?
Mm-hmm.
So yeah, and I know there were lots of houses in that area that were devastated in the and the waves. Yeah.
There's a follow-up question from Charlotte. Maybe it's the same answer. She wonders about the same thing about the narrow strip of beach between Grand Lake and Maquapet Lake Channel, Back Lake.
Oh yeah. At Indian Point.
Yeah, I think that's what she's referring to.
Well, that is also. I think that might be part of a moraine, but it's very, very washed, because that's where that big Charnockite boulder is that was in one of the slides.
Right. Yeah.
And that's on Indian Point. So the material there is different too. It's not just sand. There's a lot of fairly coarse material there.
Mm-hmm.
And if you look on the LiDAR images, it actually does look like it might be a remnant of a moraine.
Okay, so it's not a sand spit. Okay. Let me see. So now I've run out of the questions that I had recorded. I'm going to see. Okay, some comments. Excellent presentation. Awesome job, Toon, from Antoine. Locals call from Bonnie. Locals call the formation on Gagetown Island Mount Ararat, the only place that doesn't flood during the freshet.
Yeah, that's right.
That's a piece of news I never knew.
And that's why there was an old homestead on there.
Yes.
Because they knew it didn't flood, right?
Yes. Note from Chris, great presentation. Hope you can share a link to the recording later. Yes, I will be preparing the video with help from others, and we will be sharing a link to this recorded video session. Yes, something from Bernard and Christina. Mining in the Ruhr Valley area of Germany required the constant pumping of water diversion to prevent that area from being permanently flooded. So I don't know about the Ruhr Valley, but you're from Europe. You may know something about that.
Well, yeah, it's a common thing with mines.
Okay.
And in the Ruhr Valley, it was probably coal mines, because the southern part of the Netherlands has some coal mines that are related to the same geology. But when you have mines that go deep underground, they often have permanent pumping. Yeah. Yeah, and there's permanent. That's why the potash mines in Sussex don't operate anymore, because they couldn't pump enough water out to make it workable. Okay. Hopefully you can hang on for just a couple more questions. We're running to the end here, but there's a question. Is there a mapping from Bruce? A question from Bruce. Is there a mapping of projected higher water levels
from climate change for St. John River and Oromocto watershed areas? Yes, I can answer that one. The Brunswick government prepared a beautiful projected water level in 2100 mapping based on the LiDAR observations done for our province that we have a link to on our Watershed website. So anyone can go there and look up for any specific address, even the projected water level in 2100 or a 1 in 20 year flood with the current level of sea level. And it's very, very helpful. This is from Bruce Messer. Bruce, I will try to find your email and send you an answer to that question by email with a full link. That's my knowledge. You have any other comments on that, Tom?
No, I just know that the water will rise. And like I said, there are several bottlenecks in the system between Grand Lake and the Bay of Fundy that I mean, and that's one of the reasons when we looked at maybe having a spillway down in St. John. And I mean, people sort of gave a little bit of a, they briefly looked at it, but it's extremely expensive. And the other thing is, you solve that bottleneck, then there's other ones further up river that are almost as bad. So, you know, it's you really have to look at the entire system and see what you can do. And if anybody is interested, I don't know if I have a slide on that.
Do you have that room for the river slide?
Yeah, here I have a slide. I had this slide here. I and almost anticipated some of these questions. This is Nijmegen in the Netherlands, and this is the Rhine, or yeah, this is the Rhine, and it goes right through this this city of like 300,000 people. And there was a couple of near flood events in the 90s. And they calculated how much damage would have been done if it would have topped the inland dikes. And they said, well, we can't risk this happening. And so they started this Room for the River project. And you can go online, it's got a website of its own. And the Dutch government spent, I think it's 10 billion euros over the next, like from 2000 till 2008, I think. They spent 10 billion euros on creating room for the water, basically, and creating buffer zones, because they realized you start building dikes and you constrict valleys, the water will find the low spots. So if you don't create those low spots where you want the water to go, then the water will go where it wants to go. Mm-hmm. And so it's yeah, it's and this is not this is the biggest project in that Room for the River thing, but there's I think there was 40 different projects.
Mm-hmm. Yeah, so there's ways to adapt is what it boils down to. If you're willing to spend the money and do it in a a way that works with nature.
I personally think that the Dutch are living on dangerous ground, but you know.
Yeah. Yeah. Okay. One person, Chelsea Caldwell-Pash, says, I volunteer to scuba dive, underwater archaeologist here. So there you go. If you need somebody to explore underwater moraines or I guess.
Wow, that should be
you have a volunteer. Thank you.
That would be very interesting. Yeah.
Thank you, Chelsea.
What we need to do, like there's lots of room for research in those areas for sure.
Yeah. A question from Sam Longard. Hi, Toon and Brad. We are only able to join for the tail end. Will the recording be available for access later? The answer is yes, Sam. It will be available. I will send an email to everybody that registered for the webinar, letting you know when it's up on YouTube. There's a lot of, this is from Angela, and I know we should probably call it quits here momentarily, but she asks, there's a lot of clay in the area of Grand Point, excuse me, but there are also coal outflows. I've often wondered if they are part of the deeper infrastructure of boulders that are under the bar, clay and coal outflows. So maybe Angela has already dove on those areas and actually knows what's under there. I don't know the answer.
I know when you go in that area between Maquapit and Grand Lake that there are very, very thin coal layers in some of those outcrops.
Okay,
But the thicker coal is further to the north.
right. Okay, so I guess the answer, it could be yes. The answer could be yes. Is it true? Gordon asks, is it true that Oromocto Lake once emptied into the Macadavic River pre-ice age? Well, that's
I have to
way
find
beyond my knowledge. So
I have to find
Oromocto Lake, I guess.
yeah, it's one of the earlier slides. Oh, here we go.
Yeah, there it is.
Oh, so this is Oromocto Lake here,
Yeah,
and this is Macadavic, I think. Yeah.
yeah.
So the St. John, and this is probably a proglacial meltwater channel as well, and it comes through here, or it might have even come through here. I'm not sure, but it comes through here, and then it flows like it can't overtop these volcanics here. So it finds a weak zone here, and it goes through here, and then you go through Brockway here, and it has a spillway through here. Well, and then it goes off the slide, but yeah, and then it goes into McDougal Lake.
Yeah.
And McDougal Lake is further down here, and that has a very, very wide meltwater channel. So the meltwater didn't always move over to the east where the St. John is now. It came out probably at somewhere around Pokiok or something like that and started flowing south
Mm-hmm.
and found low parts in the landscape. And remember, the land was probably still tilted, right?
Yeah.
Because of the bulge and the depression of the crust.
Yes. So I guess the answer to the question, did it once flow into the Macadavic River? It's pre-ice age. The question from Gordon is pre-ice age.
Well, it's really hard to say what happened before. Like when you look at the old Keswick Loop, like the Keswick River, right, that I showed earlier on.
Yeah.
I think it's earlier than this. Oh, here it is. Like you don't know when this was. Like it's hard to date. It's it probably happened somewhere during the Cretaceous when there was a different climate. This was probably still filled in with rocks, but it's hard to. I mean, if you imagine, initially, all the drainage was from Oromocto River to the northeast. Remember, like when the basin was formed, it was all in the direction of PEI and the Magdalen Islands. So the landscape over these millions of years has changed tremendously. Like we look at today's and we think that, well, it must have always been like that, but no, this is changing all the time.
Yeah. Okay, so you can't answer at this point. It's hard to say.
That's right.
Yeah, okay. Just some general thank you. A message from Douglas Farquhar. Thank you, Toon, for tonight's presentation. I felt as if I traveled along with the glacial erratic.
Yeah.
I'm not sure what that is, but it must be a geologist's inside joke. A great revisit to your watershed. Okay, and the rest of the questions, Douglas Farquhar says, will you have a copy of the chat segments for me to review after the presentation? Douglas, we don't normally provide those, so I think the answer is no, but we will provide answers to any questions that appear in that chat segment. Yes, so a lot of thank you. And flood hazard maps, there's the index there. This is for Gordon Dow at about the 917 map. If you're Mark, if you're still here, Douglas, there's the link to the flood hazard maps from John Russell. Okay, One last question from Bruce Messer. How did Sedimentary Lake and Macadam get all the huge granite boulders? Maybe that's an easy one.
Sorry, can you?
How did the Sedimentary Lake and Macadam, which is on the border with Maine
Oh,
primarily,
right, yeah.
how did they get all these huge granite boulders?
Okay, that's because they are derived from a local granite, and they're only transported like for a very, very relatively short distance. And the reason for that is probably that the granite there is already very weathered pre-glacial times. Like, so all these boulders were already there, or they were partially there, weathered in the soil.
Mm-hmm.
And then the glaciers picked them up and they just dumped them like in Sedimentary Lake. And yeah, if you look at Sedimentary Lake, all the landforms there are elongated.
Yes.
They're like long ridges. It's one of my favorite wilderness camping spots, actually. And there's all sorts of places where you can camp on these ridges. And yeah, the transportation distance is very short, in the order of like 5 or 10 kilometers generally.
Oh, transport of the boulders, you mean?
Yeah.
Yes. Okay.
Well,
that's really...
you can find sedimentary boulders as well, and they're transported a little bit further. But
okay, so that's the answer to I guess who asked that question? Yeah, so I can't remember now. Yeah, so I guess that's it. We pretty much answered all the questions. I will get any that we didn't answer for you, Toon. It looks like there's maybe 2 or 3 that we didn't answer, but not a lot. But yeah, so I really appreciate you taking the time to prepare this presentation. It's obviously you're really passionate about this geological history and natural history of New Brunswick, and it's wonderful you could make this presentation tonight. And we will have a video of it available for all to view, probably in about a week and a half if things go well.